Hello students, welcome to this lecture. In today's lecture we will discuss theorem 1 to 2 and then we will solve example 1 to 5. So let's get started. This is disclaimer. First we will see theorem 1 to 2. Then we will see some important remarks. After that we will solve example 1 to 5. So I hope you are with your notebooks and pens ready. So now let's start. So let's starting our discussion theorem 1. So we let R be the feasible region. Okay, and feasible region means a convex polygon for a linear programming problems, and let Z equals ax plus by be the objective function. So at optimal Z, the maximum or minimum occurs at a corner point of the feasible region defined by linear inequalities. So this is due to the linearity of the objective function and constants. So then let's see theorem 2. Theorem 2 states that for a linear programming problems, the feasible region R is defined by constants and the objective function Z equals ax plus by is a linear expression to be optimized. Okay, so the theorem here it said let R be the feasible region for linear programming problems and let Z equals ax plus by be the objective function. So if R is a bounded or enclosed region, the objective function Z achieves both a maximum and minimum value within the region R. This is due to the extreme value theorem. Okay, ensuring extrema exist when closed and bounded sets. So the optimal values of the function occur at the corner points of the region R. Clear? Now we discuss the following points to be remembered. The corner point method relies on this theorem, which ensures optimal solutions occur at vertices of feasible regions. So when the feasible region is a closed polygon, the objective function Z will reach its maximum and minimum values at the vertices of the polygon. So we only need to check the value of Z at a finite number of points, the vertices, okay, to find the absolute best solution. So now let's note this point. If the feasible region R is unbounded, an optimal value may or may not exist. Okay, this means that even if the region extends infinitely, the objective function might still reach a maximum or minimum. Okay, or it might not. So a maximum value may not exist in a set if the elements can grow indefinitely. For example, in the set of natural numbers, there is no largest number. A function might not have a minimum value if its output can decrease indefinitely. Okay, so this occurs when the function approaches negative infinity without reaching a lowest point. Further, checks are required for unbounded regions covered in a later slide. Okay, so for unbounded regions, additional verification is needed. This ensures accurate results when boundaries are not finite. So now we will discuss corner point method. Okay, so corner point method is the central algorithm for solving LPPs graphically when the feasible region is bounded. Okay, when it applies when the feasible region is bounded, then corner point method is the central algorithm for solving LPPs, linear programming problems, graphically. To find the feasible region, locate the area where all constants overlap. So this region represents all possible solutions that satisfy every condition. So to find corner points, solve the intersecting line equation. Okay, each corner point is where two boundary lines meet. Use substitution or elimination method to find the coordinates. So to find the optimal solution, calculate z equals ax plus by at each corner point of the feasible region. So when the feasible region is bounded, the maximum or minimum values of z occur at the vertices. Okay, so if the feasible region is bounded, the largest and smallest values of z are the maximum or minimum values. So if the feasible region is unbounded, then check if the open half plane, that means ax plus by, is greater than m or ax plus by is less than m. Now then substitute the points coordinates into the inequality. If the inequality holds true, the point is in that half plane. Otherwise, there is no maximum or minimum value. So now we will see steps in graphical method. So to graph linear inequalities, first rewrite each inequality in slope intercept form. Y equals mx plus b. Okay, then plot the line. Use a dash line for less than or greater than and a solid line for less than equal to or greater than equal to. Okay, and then set the region that satisfy the inequality. So first your work, graph the constants as linear inequalities. Then to identify the feasible region, graph all constants on a coordinate plane, and then set the area where all inequalities overlap and select the region that satisfies every condition simultaneously. Okay, so this region represents all possible solutions to the problem. Then to find the corner points of the feasible region, identify intersection of boundary lines formed by constants. To solve all linear programming problems, evaluate the objective function at each corner point of the feasible region. Okay, so these points are intersection of constant lines. So calculate the function value at each to find the optimal solution. Use corner point method to determine the maximum or minimum. Okay, so choose the corner point that optimizes the problem objective function. Okay, so now let's look at this example. In this example, we need to solve a linear programming problem graphically. The problem provides the objective function z equals 4x plus y and three constants: x plus y is less than equal to 50, 3x plus y is less than equal to 90, and x is greater than equal to 0 and y is greater than equal to 0. Okay, and our goal is to find the maximum value of z under these constants. Okay, so first of all, try it yourself and then see solution. So let's start the solution step by step. So first look at step 1 and 2. So step 1 and 2 is for graphing the feasible region. Okay, so first, when converting inequalities to equations, we get x plus y equals 50 and 3x plus y equals 90. So the constant x plus y equals 50 is a straight line that crosses the x-axis at 50, 0 and the y-axis at 0, 50. So shading is towards the origin since 0 plus 0 is greater than less than equal to 50. Okay, so it satisfies the given inequality, that is x plus y is less than equal to 50 by putting x equals 0 and y equals 0. Okay, so that is why the shaded line towards the origin. The line 3x plus y equals 90 crosses the x-axis at 30, 0 and the y-axis at 0, 90, meaning when x is 0, that case y is 90, and when y is 0, then x is 30. So shading is towards the origin since 3 into 0 plus 0 is less than equal to 90. Okay, so in this case also, when we test origin, that is x equals 0 and y equals 0, that case it satisfies the inequality. Okay, that is why the shading is towards the origin. Then non-negativity constants, that is x is greater than equal to 0 and y is greater than equal to 0, mean that the values of x and y cannot be negative. So we only consider the first coordinate where both coordinates are 0 or positive, which limits the feasible region to the area where x and y are on the on or above the origin. So now draw the graph of x plus y equals 50 and 3x plus y equals 90. Okay, so when if y equals 0, then x is 50. So another point is 50 comma 0. So draw a line through these points. So for 3x plus y equals 90, if x equals 0, then y equals 90. So one point is 0 comma 90. Okay, so if y equals 0, then 3x equals 90. So x equals 30. So giving the point 30 comma 0. So draw a line through these points and you will get this graph. So here the feasible region is the shaded region shown in figure 12.2. So now step 3 involves finding the corner points of the feasible region, which are the intersection of the boundary lines formed by the constant. So the origin labeled as O is the point 0, 0 on a coordinate plane. And to find the y-intercept of the equation x plus y equals 50, remember that y-intercept occurs when the graph crosses the y-axis, which is when x is 0. So substitute x equals 0, which is when y equals 50. Okay, so we get this point 0, 50. So for point A, y-intercept, which is 0, 50. To find the intersection point of the lines, x plus y equals 50 and 3x plus y equals 90. Okay, so we will solve these two equations by using elimination method or substitution method. Okay, and we will find the values of x and y, and after that we will get the coordinates of the point where two lines are intersecting. So when subtracting the equation x plus y equals 50 from 3x plus y equals 90, we get 3x plus y minus of x plus y equals 90 minus 50. Okay, and it implies 2x equals 40 and it implies x equals 20. So now substituting x equals 20 into the equation, x plus y equals 50 means replacing here x with 20. So the equation becomes 20 plus y equals 50. Okay, and from here you can easily find the value of y. Okay, so 20 plus y equals 50. From here you can find the value of y, which is 30. So there is no need to solve for it. So it is already solved. Y equals 30 here. So b equals 20 comma 30. And now find point C. So x intercept of 3x plus y equals 90, which is 30 comma 0. Okay, now evaluate z and determine optimum value. Okay, so the corner points O 0, 0, point A 30, 0, point B 20, 30 and point C 0, 50. Okay, these are basically the vertices of a polygon, likely a quadrilateral formed by the intersection of linear constants in a linear program problems. So now let's look at this figure 12.2. So we evaluate now z equals 4x plus y at 3 points. So to find the optimal value of z equals 4x plus y, we evaluate at each corner point by substituting the x and y values into the equation. At point O 0, 0, z equals 0. At point A, z equals 120. At point B, z equals 110. And at point C, z equals 50. So we need to maximize z. Okay, so here we will take the value of z is 120. Okay, and this occurs at the point C 30, 0. So the maximum value of z is 120, which occurs at the point C 30, 0. Okay, so I hope this example is clear to all of you. So now let's move to the next example. In this example, we have to solve the following linear programming problems graphically. Okay, so here we need to maximize the optimal function z equals 200x plus 500y subject to the constants x plus 2y is greater than equal to 10, 3x plus 4y is less than equal to 24, and x is greater than equal to 0 and y is greater than equal to 0. Okay, and our goal is to find the minimum value of z by graphically. So let's start the solution step by step. So to graph the feasible region, first rewrite each inequality as an equation to find the boundary lines by solving for y. So when converting inequalities to inequations, we get x plus 2y equals 10 and 3x plus 4y equals 24. So now constant 1, x plus 2y equals 10. Intercepts are 10, 0 and 0, 5. And here setting is towards the origin since 0 plus 0 is less than equal to 10. And look at constant 2. So 3x plus 4y equals 24. So the intercepts of 3x plus 4y equals 24 are 8, 0 and 0, 6. So setting is towards the origin since 3 into 0 plus 0 is less than equal to 24. So now check non-negative constants. Here x is greater than equal to 0 and y is greater than equal to 0. And it restricts the region to the first coordinate. So now draw the graph of x plus 2y equals 10 and 3x plus 4y equals 24. Okay. So here let's look at this graph, figure 12.3. So here the feasible region is the shaded region shown in the figure 12.3. So now let's identify the corner points. So first find corner point A, that is y-intercept of x plus 2y equals 10, which is 0, 5. And the point B, the point B of the lines, basically it is intersection of x plus 2y equals 10 and 3x plus 4y equals 24. Okay, so B point is basically intersection point of the lines x plus 2y equals 10 and 3x plus 4y equals 24. So now to subtract 2 times x plus 2y from 3x plus 4y, we get 3x plus 4y minus 2 times x plus 2y equals 24 minus 20, and from here you will get the value of x is 4. Okay, so it implies x equals 4. Now substituting x equals 4 into the equation, 3x plus 4y equals 24, and then we get 12 plus 4y equals 24. Okay, so from here you can easily find the value of y. So it implies 4y equals 12 and it implies y equals 3. And the equation y equals 3 represents a horizontal line on a coordinate plane. And so B point is located at the coordinates 4, 3. Now find the point C. The point C is basically the y-intercept of 3x plus 4y equals 24, which is 0, 6. Now we need to evaluate z. Determine the optimum. First calculate the value of the objective function z at each corner point of the feasible region by substituting the coordinates into the equation. So the corner points are A 0, 5, B 4, 3 and C 0, 6. Okay, these are the vertices of a polygon, likely a triangle, where each point represents a specific location on the coordinate planes. So now we evaluate z equals 200x plus 500y at these points. So now find corner point A, B, C. Okay, and here we need to evaluate the value of z equals 200x plus 500y. Okay, so the value of z at point A is basically 2500. Okay, and the value of z at point B is 2300. Okay, and the value of z at point C is 3000. Okay, and here we need to find the minimum value of z. So the minimum value of z is what? Here which value is minimum value? So here the minimum value of z is basically 2300. Okay, and which occurs at the point B 4, 3. Now we discuss LFPs with unbounded feasible region. If the feasible region is unbounded, a maximum or minimum value of the objective function may not be exist. Okay, however if it does, so it must occur at a corner point. So to solve problems over unbounded regions, we use techniques like Laplace transform or Fourier analysis. Okay, that you will learn in higher class. So method for unbounded regions. So here you should follow steps 1 to 4 of the corner point method. to find the corner points and evaluate Z. And then let m be the maximum value and small m be the minimum value of Z from the corner points. So for maximization, we seek the highest value of a function, often using derivatives to find the critical points. Okay, so to maximize Z equals ax plus by, graph ax plus by is greater than m, and if this region has no overlap with the feasible area, then m is the maximum value of Z. Okay, and then case A, if this open half plane has no points or in common with the feasible region, then the m is the maximum value. And then see case B, so if this open half plane has points in common with the feasible region, then the problem has no maximum value. For minimization, if you want to minimize Z equals ax plus by, graph the open half plane ax plus by is less than small a. So if this plane if this open half plane has no points in common with the feasible region, then small m is the minimum value. And case B, if this open half plane has points in common with the feasible region, then the problem has no minimum value. Now let's see this example. So here in this example, we need to determine graphically the minimum value of the objective function Z equals minus 50x plus 20y, subject to the constants 2x minus y is greater than equal to minus 5, 3x plus y is greater than equal to 3, and 2x minus 3y is less than equal to 12, and x is greater than equal to 0 and y is greater than equal to 0. So first of all, try it yourself and then see solution. So let's solve this example step by step. So step 1 and 2 for graph the feasible region. So on converting inequalities to equations, we replace the inequality symbol like less than, greater than, less than equal to, greater than equal to with an equal sign, which helps us find the boundary value where the inequality changes from true to false. Okay, so to solve the system of equations, 2x minus y equals minus 5, 3x plus y equals 3, and 2x minus 3y equals 12. So here constant 1, 2x minus y equals minus 5. First rewrite it as y equals 2x plus 5 by adding y to both sides and then adding 5 to both sides. Then find the intercepts. When x equals 0, it implies y equals 5. Okay, and when y equals 0, that case x equals minus 2.5. So we set the region where 2x minus y is greater than equal to minus 5, that is actually above the line. So then see constant 2, 3x plus y equals 3, so we can rewrite this as y equals 3 minus 3x. So then find intercepts. X equals 0, it implies y equals 3, and y equals 0, it implies x equals 1. So we set the region where 3x plus y is greater than equal to 3, that is above the line. So for constants 3, 2x minus 3y equals 12, so we can rewrite this as y equals 2x minus 12 divided by 3. Then intercepts, when x equals 0, then y equals minus 4, and y equals 0, then x equals 6. So we set the region where 2x minus 3y is less than equal to 12, that is below the line. Okay, and then non-negativity constant, that is x is greater than equal to 0 and y is greater than equal to 0. These restrict the region to the first coordinate. So now draw the graph of 2x minus y equals minus 5 and 3x plus y equals 3 and 2x minus 3y equals 12. So this is our graph. Okay, here we have drawn the graph of 2x minus y equals minus 5, 3x plus y equals 3 and 2x minus 3y equals 12. Here the feasible region is the saddle region shown in this figure. So step 3 is to identify the corner points. So the point A, this is where the y-axis, that is x equals 0, intersects with the line 2x minus y equals minus 5. When x equals 0, substitute 0 into the equation for x, which gives minus y equals minus 5. So y equals 5. Then when x equals 0, that case we get here y equals 5. So therefore the point A is 0, 5. Now find point B. This is where the y-axis, that means x equals 0, intersect with the line 3x plus y equals 3. Okay, when x equals 0, it implies y equals 3. Therefore, the point B is 0, 3. Now find point C, where the line 3x plus y equals 3 crosses the x-axis. That means y equals 0 in this case. So remember that when the x-axis, the y coordinate is value 0. So substitute here y equals 0 into the equation. So 3x plus 0 equals 3. From here we will get the value of x. So when y equals 0, it implies 3x equals 3. So x equals 1. Therefore, the point C is 1, 0. Now to find point D, where the line 2x minus 3y equals 12 crosses the x-axis. Remember that when the x-axis, the value of y is value 0. So so substitute y equals 0. So you will get 2x minus 3 into 0 equals 12, which simplifies to x equals 6. Therefore, the point D is 6, 0. So first of all, let us graph the visible region of the system of inequalities 2 to 5. Okay, so this is our graphical representation of the given constants. The feasible region, that is here shaded region, that is shown in the figure 12.5. So here observe that the feasible region is unbounded. So we now evaluate Z at the corner points. So step 4 and 5 for evaluating Z and determine optimum. So the corner points are A 0, 5, B 0, 3, C 1, 0 and D 6, 0. So we evaluate Z equals minus 50x plus 20y at these points. So to find the optimal value of Z equals 4x plus y, evaluate Z at each corner point at point A 0, 5. Okay, so the value of Z at point A is basically 90. So the value of Z at point B is 60. The value of Z at point C is minus 50. The value of Z at point D is minus 300. Okay, so here we evaluated the values of Z at point A, B, C and D. So from the table we find that minus 300 is the smallest value of Z at the corner point 6, 0. So here note that if the region would have been bounded, the smallest value of Z is the minimum value of Z. Okay, but here we see that the visible region is unbounded. Therefore, minus 300 may or may not be minimum value of Z. To decide this issue, we graph the inequality, which means we draw a visual representation of all the solutions that satisfy the inequality on a coordinate plane. To solve the inequality, minus 50x plus 20y is less than minus 300. So first simplify by dividing all terms by 10 to make it calculation easier. So the resulting inequality will become minus 5x plus 2y is less than minus 30. Then check whether the resulting open half plane has points in common with feasible region or not. So if it has common points, then minus 300 will not be the minimum value of z. Otherwise, minus 300 will be the minimum value of z. So, as shown in figure 12.5, it has common points. Therefore, z equals minus 50x plus 20y has no minimum value subject to the given constants. Now, we discuss when does it happen. So, this occurs when the set of constants are contradictory. So, there is no point x comma y that can satisfy all the given constants simultaneously. In that case, it may happen. Okay, and how to identify it? So, when you graph the inequalities representing the constants, you will find that there is no common shaded region. The feasible region is an empty set. So, now we will conclude, since there is no feasible region, there are no feasible solutions. Therefore, the problem has no solution. Now, let's look at this example. Here in this example, we have to minimize z equals 3x plus 2y subject to the constants x plus y is greater than equal to 8 and 3x plus 5y is less than equal to 15 and x is greater than equal to 0 and y is greater than equal to 0. So, let's start the solution step by step. So, step 1 and 2 is to graph the feasible region. So, on converting inequalities to equations, we replace the inequality symbol like less than, greater than, less than equal to, greater than equal to with an equal sign to form an equation. So, we get x plus y equals 8 and 3x plus 5y equals 15. To solve the constant x plus y, we can rewrite it as y equals 8 minus x. Okay, and here are intercepts. When x equals 0, then y equals 8, and when y equals 0, then x equals 8. So, we set the region where x plus y is greater than or equal to 8 above the line. Now, let's look at constant 2. 3x plus 5y equals 15. So, here we can rewrite it as y equals 15 minus 3 divided by 5. So, here intercepts x equals 0, that implies y equals 3, and y equals 0, then x equals 5. And we set the region where 3x plus 5y is less than or equal to 15, and here it is basically below the line. And then non-negativity constants, x is greater than or equal to 0, y is greater than or equal to 0. These restrict the region to the first corner. Now we draw a graph of x plus y equals 8 and 3x plus 5y equals 15. And this is our graph. Okay, so let's look at figure 12.6. And now let's identify the corner points. Point 0, 8, intersection of the y-axis when x equals 0 with the line x plus y equals 8. When x equals 0, then y equals 8. Okay, and point 0, 3, intersection of the y-axis, that means x equals 0 with the line 3x plus 5y equals 15. Then when x equals 0, then 5y equals 15, so y equals 3. Then point 5, 0, intersection of the x-axis y equals 0 with the line 3x plus 5y equals 15. When y equals 0, 3x equals 15, so x equals 5. Then point 8, 0, intersection of the x-axis, that means y equals 0 with the line x plus y equals 8. When y equals 0, then x equals 8. Then let us graph the inequalities 1 to 3. So that is shown in figure 12.6. Okay, so let's look at this figure 12.6. And here from figure 12.6, you can see that there is no point satisfying all the constants simultaneously. Thus, the problem is having no feasible region and hence no feasible solution. Now, we discuss remarks from the examples which we have discussed so far. So, we notice some general features of linear programming problems. Okay, so the feasible region is always a convex polygon, convex region. Okay, and the maximum or minimum solution of the objective function occurs at the vertex or corner points of the feasible region. So if two corner points uh, produce the same maximum or minimum value of the objective function, then every point on the line segment joining these points will also give the same maximum or minimum value. So now what does it happen? Okay, so if the objective function z equals x plus by is parallel to the feasible region edge, then multiple points along that edge yield the same z value, okay, leading to infinitely many optimal solutions. So how to identify it? So after using the corner point method, you will find the optimal or optimal, that means maximum or minimum, is achieved at two adjacent corner points. Okay, for example, if z max is 120 occurs at both a point x1 comma y1 and b x2 comma y2, then what is the solution? So the optimal value z max equals 120 occurs not just at points a and b, but at every point on the line segment ab. So any point x comma y in the line segment between a and b is an optimal solution. So now let's look at this example. In this example, we have to solve the following problem graphically. Okay, so here we have to minimize and maximize z equals 3x plus 9y subject to the constants x plus 3y is less than equal to 60, then x plus y is greater than equal to 10, and x is greater than equal to y, and x is greater than equal to 0, and y is greater than equal to 0. So first of all, try it yourself and then see solution. So let's start the solution step by step. On converting inequalities to equations, we get x plus 3y equals 60 and x plus y equals 10 and x equals y. So start by substituting x equals y into the second equation. So now step 1 and 2, graph the feasible region. So constant 1 we will get from equation x plus 3y equals 60. So the intercepts are 60 comma 0 and 0 comma 20. And here setting is towards the origin since 0 plus 0 is less than equal to 60. And then let's look at constant 2, x plus y equals 10. So it is a straight line that crosses the x-axis at 10 comma 0 and the y-axis at 0 comma 10. And here setting is away from the origin since 0 plus 0 is greater than equal to 10. Then let's look at constant 3. So here x equals y. Okay, so setting is below the line since x is less than equal to y. So now non-negativity constants x is greater than equal to 0, y is greater than equal to 0 restrict the region to the first coordinate. So now graph the region x plus 3y equals 60 and x plus y equals 10 and x equals y. So let's look at this figure 12.4. So this is actually graph of the equation x plus 3y equals 60, x plus y equals 10 and x equals 1. Now step 3 is to identify the corner points. So B point intersection of x plus y equals 10 and x equals y, which is 5 comma 5. And C point intersection of x plus 3y equals 60 and x equals y, which is 50 comma 50, 15 comma 50. The point C, the point C, which is basically intersection of x plus 3y equals 60 and x equals y, which is 15 comma 15. Okay, and the point D, which is intersection of x plus 3y equals 60 and x equals 0, from x is greater than equal to 0 and y is greater than equal, which is 0 comma 20. And the point A, intersection of x plus y equals 10 and x equals 0, which is 0 comma 10. Okay, and this is our graph of the given equation. And now step 4 and 5, evaluate Z and determine optimum. So the corner points are A 0 comma 10, B 5 comma 5, C 15 comma 15 and D 0 comma 20. We evaluate Z equals 3x plus 9y at these points. And here let's look at this corner point and the corresponding value of Z. Z equals 4x plus y. Okay, so at point A, the value of Z is 90. At point B, the value of Z is 60. At point C, the value of Z is 180. And at point D, the value of Z equals 180. And we now find the minimum and maximum value of Z. So from the table, we find the minimum value of Z is 60 at the point B 5,5 of the feasible region. The maximum value of Z is on the feasible region occurs at the two corner points C 15,15 and D 0,20, and it is 180 in each case. So any point x, y on the line segment connecting C and D is an optimal solution. Clear? I hope it's clear to all of you. So that's all for today's lecture, and thank you very much to all of you.